So welcome back everybody to our Gamma seminar. Today we have the pleasure to get Roberto Rubio from the Universitat Autónoma de Barcelona. He's going to talk about on higher Dirac structures. So Roberto, thank you for accepting our invitation. It's a pleasure to have you here. So please, the floor is yours. Go ahead.
Okay, so well, thank you for inviting me to this seminar. Really, like you set up a great seminar. I don't come here, but I see your videos online. So yeah, and I saw also that there is a lot of discussion. And I saw actually that last week there was even a question about what I'm going to talk about today. So what I'm going to talk about is some kind of old work. It was published like 2019. Probably we posted the first version in 2016. It is joined with Enrique Bursztyn and Nicolás Martínez-Alba. And so the fact that it's a bit old, it may be actually be positive as well, because I may focus more on the insights rather than on the technicalities. But I apologize up front in case I'm like I forgot about some details. And also for the connection with physics, yeah, that's not my strong point. So yeah, I trust the people who know. I mean, this is helpful, and I'll do my best. It's going to be dense because it's quite heavy. So I won't promise to make a light talk. I will try to make a short talk at least. So having said this, let me get started, and let me start by the Hamiltonian formalism. So I like to think about this as the equation of like Newton's law, reinterpreted as a symplectic structure. So this is for me the Hamiltonian formalism, and then when some other conditions appear here, like you have some constraint or you have some symmetries, then is when presymplectic and Poisson structures appear. Of course, a natural question is what happens when you have both symmetries and constraints on your mechanical system, and this was answered by Courant, student of Weinstein. And the answer to this is Dirac structures that you talked about last week. So these are subbundles of this Tm plus T star m, which are Lagrangian for the natural canonical pairing. So here I put the quadratic form, but of course, here you can just think that if you have now two elements, x plus alpha for me will be a section of Tm, well, an element here of Tm plus T star m. Sometimes it will be a section. So, and you have y plus beta. So this will be 1/2 of, now you just have to pair alpha y plus beta x as usual. Okay. So,
Roberto.
yes.
You know, we make a lot of questions, don't you?
Yes. Okay, great. Yeah.
Why do you use the quadratic? I mean, normally, I really confess that it's one of the few times I have said it. If there is any reason to do this way instead of just
I said it with a quadratic, you know, but like because this formula is a bit like long, like the pairing. So I think this is kind of very compact. So by just polarization, you get the usual pairing. So that's why I stated it with the quadratic. It's just if you want aesthetics.
To make it, okay, because you know, one adds some structure, always is thinking if there is something special about it. Okay, thank you.
So now, okay. Yeah, when I have some, I consider Lagrangian subbundles for Tm plus T star m, it turns out that the examples I had before, or the extremal cases I had before, will appear as particular instances of these Dirac structures. And of course, here I'm using like the usual notation, like if Poisson is a bivector, so now this thing here will be something that will take an element of T star m to Tm, and here I will get an element of Tm T star m for this omega flat. And the fact that they are Lagrangian is actually capturing the fact that they are skew symmetric in both cases. apart from being Lagrangian, which is just a linear algebraic condition that can be described at each single point, we have a geometric condition. And this geometric condition is stated in terms of this very magical bracket for me, which is the Dorfman bracket. Here I'm giving the non-skew symmetric version, but that satisfies a nice Jacobi identity. So this is the integrability of this structure. This should be thought in the same way as foliations, distributions are integrable when they are involutive with respect to the Lie bracket, and then they give rise to a foliation. So here we have that Dirac structures are integrable when they are involutive with respect to this bracket. This is a kind of magical bracket because it happens that asking the subbundle L in Tm plus C star n to be involutive means that in the two examples I had this graph of the symplectic form, this graph of the graph of the presymplectic form and the graph of the Poisson bivector will give me actually that presymplectic it gives me, here it doesn't need to be presymplectic still, and the Poisson is just a bivector. So it gives me, it captures essentially the fact that omega is closed and that the Poisson bivector is actually integrable, which is stated usually in terms of the Schouten bracket. Okay, so
just one, may I add a question, Roberto? You know, you can characterize the Dirac structure geometrically by saying that it is a stratified space into presymplectic leaves. So do you know if there is any relation of that with characterizing the Dorfman of the Courant bracket as they are done? And then do you know if the Dorfman or Courant bracket can be constructed in such a way that they will be closed when there is some kind of stratification by presymplectic manifolds?
So, I mean, when I explain this in some courses, kind of I try to derive the bracket in a heuristic way for that to happen. But okay. I don't have, say, some sort of kind of universal property or whatever to make a strong statement like that. Yeah.
Okay. Thank you. Because I was curious. I kind of tried something like that, but at the very end, it was always heuristic. I mean, it's a certain moment at which I have to suppose some kind of by hand condition on the bracket.
I mean, I guess it depends how much you allow yourself to adjust things. But I guess if you start by saying, yeah, I want involutivity for this bracket to give me leaves, then probably you have that, okay, already the projection to Tm has to be the Lie bracket, okay? So if there is an analogous result to what you are saying.
Yes. This is the way I thought, more or less.
Yeah, and then like if you want, to capture that they are presymplectic, I think, kind of the by the formula of Alex it's like at the end of the day, I mean, I think, let me annotate this. Yeah, I think there is like, because you have this in here, and somehow, here now you can put there was, I mean, I have it in some notes somehow, like, because I didn't want to give people just this bracket. I said, okay, if I want a bracket that will capture the it's actually more like the integrability of the graph, but I guess then you have to assume that you want to do it through the graph.
Yeah, you have a foliation, and with these foliations, you consider somehow the vector fields, and you want to map them into the cotangent. And it's not uniquely defined because indeed you have different brackets. You have the Courant, you have the Dorfman, and so on. But if you want somehow to be described, I mean, something antisymmetric at the very end, down to something like that.
Yeah.
Okay.
But bear in mind, when you say you have the Dorfman, you have the Courant, but if you ask it to satisfy the Jacobi identity, so then you will have I guess you will only have the Dorfman.
Yeah,
So,
yeah, sure.
so that can make it unique actually. But yeah, I would say, I mean, I think you can fit it, but still, it would feel a bit heuristic. Yeah, I don't know if there's something very like a strong kind of universal.
Okay, but thank you for your answer. I was curious about it. Thank you.
Okay, so now I have to review something about Dirac structures in order to talk about higher Dirac structures. And this is, let's see if this, yeah, okay. Now I can see, yeah, now I can see I have to delete all the annotation, which I hope it's easy, clear. Okay, good. So, okay, so I want to describe Dirac structures, and the motivation is actually the graph of a two-form of a presymplectic structure. Okay, so this is the graph, and I would like to do the same for every Dirac structure. So in order to do the same for that, I will use the projection to Tm to know what are the possible vectors that appear on my Dirac structure, and I will consider this E, which is just the projection on the Tm. So where L here is an arbitrary Dirac structure. Now, when I have X in E, which I say, okay, it's some projection of some element in L, it turns out that in general, it's not a graph. It's not like the symplectic, like the presymplectic structure, where it is a graph. Okay, here there may be several alphas, such that X plus alpha is in L. So what I'm going to give is a graph like that. Okay, that's my target. I want for each X to give all the possible alphas such that X plus alpha is in L. So here there are two key points, which are, first of all, if I have an element X plus alpha already in L, X plus alpha prime will be in L as well, if and only if the difference of the alphas belong to L, of course, because is in, I'm subtracting two elements in L, and because I cancel the X, so it also is in T star M, okay? So this is just the first condition. Now the second condition, the second key point, the second fact is that actually this intersection of L intersection with T star M is going to be the annihilator of E. Now, here there is something very important to say, which is the fact that L intersection with T star M is inside the annihilator of E, this happens always for any isotropic subspace. The fact that it is exactly the annihilator of E, it happens because it is maximally isotropic. So you could always say, okay, if it's not the whole thing, then I would add the annihilator of E, and the whole thing will still be like isotropic. So you would make it maximally isotropic. So these are the two key facts in order to describe Dirac structures as I'm going to do now, which is, as I said, for each X, I want to give all the possible alphas. But what I'm saying here is that all the possible alphas are actually a co-class for the annihilator of E. So any X in E, I have to send it to some alpha plus annihilator of E, some co-class here. Okay, so this is the map whose graph will be the Dirac structure somehow. And this map, I can write it as a map from E to E dual, because precisely T star M modulo the annihilator of E is E dual. And it happens that for this graph to be isotropic, I need this epsilon to be in wedge 2 of E dual. Okay, and now how do I define the graph of such a thing? So this is actually this usual description, LE epsilon. And LE epsilon are elements X in E and all the alphas belonging to that class. And actually this, I can write it as the restriction of alpha to E being epsilon of X, okay? All these are Lagrangian when epsilon is here, a wedge 2 of E dual, and actually any Lagrangian is of this form for any choice of E and for any epsilon.
Sorry, Roberto, one question. In the case of integrable Dirac structure, the E, the generalized vector bundle, will be integrable. So the annihilator will be a Pfaffian system, yeah?
Yeah, here, bear in mind, I'm saying here at a point. I'm actually
integrable. Yeah, I mean a point. Yeah. I mean, if you consider globally with Dirac structure when it's integrable, yeah, the alphas will be the forms vanishing on an integrable distribution. So they will give you an integrable Pfaffian system. Yeah, there are one forms, and the differential of these forms will be zeros in the distribution. Yeah, something like that.
I'm not familiar with the theory.
I mean, when you characterize distributions or generalized distributions by means of one form that vanishes on them, yeah. If I don't remember it, if I properly remember it, the fact that the distribution, the distribution, at least the regular case, is integrable, okay, amounts to the fact that the alphas you have, the differential of the alphas, will be included in the ideal expand by these alphas. I mean, if you pick up the differential of any of these alpha, like a section, okay, defined on different points, the differential will be always contained factorized by means of the section of the.
Okay, but I guess that will be equivalent because you are talking about the regular case for this epsilon to be actually closed for the Lie algebraic differential.
Yeah, this case it will be epsilon close in which
for the Lie algebraic differential, like
Lie
algebraic in your regular case.
I mean, it does not need to be closed, but there are. Oh yes, it's. Well, I'm not sure because there are
in the regular case. I mean, this is Courant's word. Say in the regular case, E has to be
close,
a Lie algebraic, and then this epsilon has to be close.
Okay, so
the algebraic differential, and I guess that can be written in the terms you are saying.
No, probably. Okay, thank you.
Okay, so yeah, these are the LE epsilons. So yeah, I mean, this is classical Dirac structures theory. But if you have any questions, it's a good moment. One last comment I want to make here is that the Dirac structures that are transversal to T star M, well, like intersect trivially T star M. So you can put as a graph of something going from Tm to T star M, and actually they are going to be graphs of symplectic, perisymplectic forms. And on the other side, we have that when they intersect trivially Tm, they're going to be graphs of Poisson structures. Okay, so now we go higher finally. So the idea is now that in the same way that we took like the second law of Newton and we said, okay, we get to symplectic, this is a Hamiltonian formalism. So now you want to do this, okay, for field theories, and you go to multisymplectic, okay? What is multisymplectic? Now, multisymplectic, instead of having like a 2 form, I will have a k plus 1 form. Now, symplectic is non-degenerate. But here, okay, how do you make sense of non-degenerate? So you're going to ask this omega flat, which you consider as a map from Tm to wedge k of T star M, to be injective. This is the non-degeneracy condition, this is the linear algebraic condition, and you add to this an integrability condition, the omega equals 0. Okay, so now a naive approach to go higher, and here I think I'm missing something, okay. A naive approach to go higher is to think about the graph of omega flat, okay, and see what kind of properties does it have. So the graph of this omega flats is going to be a subbundle now of Tm plus wedge k of T star M, and it's going to be Lagrangian Lagrangian for a pairing which is a bit special. Okay, and the pairing, when I say this, bear in mind that, okay, sorry, no, sorry, something very funny happened now. Let me see if I can go back. Wow. Okay. Yeah. Okay. So this graph of omega flat is going to be as a bundle here, and bear in mind that now the pairing that I wrote by hand before, okay, that it was something like x plus alpha y plus beta equals 1/2 of alpha y plus beta x. Now, okay, actually here I should probably write more like the contraction thing. Okay, these are elements in wedge k. So actually this whole thing is going to be in wedge k minus 1 of t star n. Okay, but still I can make sense of something being orthogonal for this pairing. Okay, I won't be able to measure much, but I can say when things are orthogonal. Okay, so you can give this as a first attempt to say, okay, how am I going to generalize Dirac structures to higher situations? To say, yes, in the same way that you took the graph of a symplectic, presymplectic structure, just take a graph of a multisymplectic structure. And it turns out it is Lagrangian. See, that's very nice. And it turns out also that for the bracket, that now it will also take some it is the same formula. Okay, now the lead derivative is actually here, like giving you values in wedge k, which is where it should be, this lx beta minus iy alpha. And it turns out that actually the integrability condition of your multisymplectic form, d omega equals 0, it corresponds to involutivity with respect to this higher Dorfman bracket. And you could have a definition of higher Dirac like this. And this is actually what Marcos and Bon did in a paper that contains higher analogs of Dirac structures. And he actually cited here
sorry,
the
Roberto,
yes.
Sorry, another question. When you talk about higher analogs, is just that it's about this higher order differential forms, or Marco proposed other brackets or other stuff?
Well, I mean, now I can't remember if he uses the Dorfman or the Courant bracket, okay? But the definition but it will be the same. The definition of higher Dirac will be a subbundle of Tn plus wedge k t star m, which is Lagrangian for this pairing, which is involutive with respect to the higher Dorfman brackets. And somehow the inspiration for that are these multisymplectic structures. And then he moves on actually to the study of the L-infinity algebras associated to them, even though they have to do more like with the fact of being involutive than of being actually Lagrangian. Yeah. So that studies.
Thank you.
In general. Okay. So now if I give that definition of higher Dirac, we can see what happens, what fits there somehow. And the thing is that when you take a Lagrangian and involutive for this in this setup, if the intersection with t star m is 0, then you actually recover the graph of a multisymplectic form. And you may wonder, okay, what happens when the intersection with Tm is 0? Should I define that as higher Poisson structures? And okay, you get something, but the fact is that a bit later, some people thought about what higher Poisson should be. And it was better to look at the geometry and to regard that in the same way that Poisson structures can be seen as infinitesimal versions of a symplectic groupoids, that actually higher Poisson should be an infinitesimal version of a multisymplectic groupoid. And when you do this, when you stick to this, the definition you get of higher Poisson is this one here by Bursztyn, Cabrera, and Iglesias. Okay, so you get as a bundle of wedge k, of T star M, and some bundle map going from S to Tm, such that, and here I'm using this not notation to talk about the annihilator of a subset of forms. Okay, these S naught are the vectors such that they annihilate the whole of S. First condition, this S naught has to be 0. Second condition, this lambda has to be skew in the sense it can be skew. And the third condition is some integrability condition. It's actually that this bundle S has to be involutive for these brackets that you can put here with the lambda, and also that this map lambda has to be bracket preserved. Okay, as such, the definition looks quite complex. Let me at least tell you why it makes sense that you have to consider this S, this subbundle. Okay, because in principle, yeah, one could have thought, okay, now come on, you should go like something going from wedge K to Tm or something, and that's it. The thing is, this definition allows you to take a multisymplectic structure, okay, that since it is injective from Tm to wedge K, you can consider its image, and that image, you can consider it as this subbundle S, okay? And then, of course, if you restrict to that image, this omega flat will be invertible there. And then you will be able to consider the inverse of a multisymplectic structure on its image, okay? And this is actually kind of, if you want, a heuristic reason why it has to be like this, the definition of higher Poisson. Okay, apart from they did the math and this is what you get, but there is a reason why you must add this complexity if you want to have this somehow these inverses of multisymplectic structures. Now, the thing is that when you look at these S lambdas here, as these higher Poisson structures, and you look at their graph, look at the graph of lambda, okay, it's a map going from wedge K from a subset of wedge K to Tm. It actually lives in Tm plus wedge K T star M. So you may expect, okay, great. So that should be Lagrangian. But the reality is that it is not Lagrangian. Not always Lagrangian, okay? And this is actually the starting point of the thesis of Nicolás Martínez-Alba, who was a student of Enrique Bursztyn. And they started to see what happened here for this higher Poisson, because they didn't fit in the Lagrangian formalism. Okay, so let us restart with the going higher thing. Okay, so we said from field theories, we get to multisymplectic. Okay, now with multisymplectic, the idea should be a bit of, I want to be able, with my higher Dirac, not just to say, okay, consider now Lagrangian for wedge K, no. We wanted with Dirac to describe symmetries and constraints. So here, when I have multisymplectic and I have constraints, okay, the form may become like perhaps non-injective where it should be, and then you will have like a multi-press symplectic. Here I'm writing K-press symplectic, but it's just multi-press symplectic. But when you have symmetries, you can see actually, and there is an example also on our paper that, and I guess what is the same in the higher Poisson, that what you get is a higher Poisson in the sense I've introduced it, okay? So if we want to have a concept of higher Dirac that describes these symmetries constraints, it cannot be Lagrangian, okay? Because the graph of lambda is not Lagrangian. But they realized that the graph of lambda is weakly Lagrangian. So this means, first of all, that it is isotropic. And second, that it's not that L equals L paired, but when you intersect with Tm, they will be equal. And the interesting thing is that when K equals 1, this coincides with the usual notion of being Lagrangian. Okay, so if for some reason we should have we have defined Lagrangian by these two properties, the generalization would be direct. It would be just, okay, now we do higher Dirac with this Lagrangian condition and everything fits, okay? But the thing is that there are actually like 3 conditions that are the same for K equals 1, but they differ when we go to higher K. Okay. The definition of higher Dirac that will contain higher Poisson will be then some weakly Lagrangian subbundle of Tm plus wedge K of T star M, okay? And this way we'll have that both the graph of a multisymplectic and the graph of a higher Poisson are weakly Lagrangian, and the integrability condition is the same, involutivity with respect to higher Dorfman. And you can see that actually this condition is the one that gives you that omega will be closed, and also that this S lambda will be integrable in the sense that I described in the previous definition. Okay? So this is the definition of higher Dirac that contains higher Poisson. And now, for me, the question is how to describe the geometry. And this is somehow when I entered the picture, was when I was in the thesis committee, and yeah, I felt that we had to go back to how things were done in Dirac and try to draw an analogy here. So for Dirac structures, what I told you before, this LE epsilon, as it was already mentioned, upgrades to something geometrical. Okay, you have an integrable distribution, doesn't need to be regular, it can be singular, and you will have on each leaf a presymplectic form. Okay, and somehow precisely being of the leaf means that the distribution on the leaf is precisely the tangent to the leaf. Okay, so now the idea is what can we do now for higher Dirac? Because they are not even Lagrangian. I don't have the description like I could think, okay, can I say something similar? I mean, I have now two conditions, the isotropy and this thing here. So, and actually there is a major issue here, which is everything worked quite well in the Lagrangian case, because L intersection in that case T star M was the annihilator of E, because it was Lagrangian, and that was a key point there to have such a simple description. Now, what we can say is that L intersection wedge K will be in the annihilator of E. But I don't know whether the annihilator of E will be inside the other one, okay? So in order to describe now this weakly Lagrangian, and actually what I'm going to describe are first isotropic subspaces, we can do the following. So consider the same thing I had before, which is the projection of L to Tm, okay, this E, and consider this intersection, which I say is not an annihilator of E, is strictly smaller, okay? So I don't know what it is exactly, but I have to add it somehow if you want as a variable, and I'm going to call it AL. So somehow the annihilator part of L. Well, okay, so I have these two ingredients now. How I'm going to describe isotropics with E and AL. So I'm going to do the same thing I did before. So the same thing I did before was that, you remember I said, I'm going to try to see for each X in E, how many like alphas, what are the alphas that can go with it? So here I do the same. I say for X plus alpha in L, and here works the same, is X plus alpha prime will be in L if and only if the difference of the alphas, because I can take the X plus alpha minus X plus alpha prime, so that gives me alpha minus alpha prime, that's an element of L, and that's an element of wedge K, and that's precisely what I defined as AL, okay? So here, I cannot say this is an annihilator of E, but it's something else, something there in the middle, between 0 and annihilator of E. So I have that I can consider a map as before, epsilon, going to the co-classes for AL. So this map, epsilon of X, will give me some alpha plus AL, only if and only if X plus alpha is precisely in this isotropic subspace, okay? So before, remember, AL was an annihilator of E. So you could transform this whole thing on the right into E dual and then talk about epsilon to be skew and get wedge 2 of E dual. Now we need an analogous condition. And when I consider this L, E, A, L, epsilon, which are the elements x plus alpha such that x is in E, and the alpha is in the image of this map, okay? I will make sure that this is isotropic when I do an analogous condition to this wedge 2 of A dual. And this you do by using this map here, this jota-E. What is this jota-E doing? So this thing, when you give it one of these co-classes, okay, the co-classes are all the possible alphas that can go with some x. Okay, when you give one of these co-classes, you can map that to a map that goes to an element of E dual tensor k minus 1. And here, sorry, I put the V notation. V should be here Tm. Okay, so this should be here Tm, and here Tm. So now, because I do the contraction of this alpha with an element of E, and AL I know is inside the annihilator of E, okay, the k minus 1 form that I get does not depend on the representative alpha. Okay, what I'm saying is that somehow for any element in alpha plus AL, when you contract by an element of E, you always get the same k minus 1 form. Okay, and once you've done this, you can actually talk about some kind of being skew for this E. So now you can say that the map that we defined before, this epsilon that gives you things as a graph, will be E skew precisely when I compose with this map and the thing I get is actually wedge 2 of E dual tensor the k minus 1 forms. And this is the way that you capture this thing being isotropic. Okay, so now this way epsilon will be E skew, and every isotropic will have an E skew epsilon. And this is the equivalent description of isotropic subspaces. Actually works also for k equals 1. Okay, is the analogous description to the LE epsilon, but just for isotropic subspaces. Okay.
May I ask a comment,
Sure.
maybe? I was thinking about this in a particular example. For example, when L is described by means of Poisson structure, okay, the normal one, the Dirac structure. So in that case, your AL, it could be something that they are the differential of the Casimir functions. They are things that they vanish. And the isotropic would be that the contraction with vector fields, they vanish on this vector field. So is something related to this? Is some kind of Casimir operator? Because it looks like a generalization of this differential for something of higher order. Have you thought of this like?
No, I haven't explored that. Yeah, this is very linear algebraic, I must say.
Yeah.
So far, what I'm doing. Okay, I would, yeah. I mean, the way I understand it, I don't know if it has other consequences, but it's just that this thing that, okay, you don't have, since it's not maximal, you cannot ensure that annihilator of E is there, and you have to control where it is. It could be.
Yeah, because you have the maximality, well, dimensions that do not fit. Yeah, when you have the distribution in the direct case, the annihilator, it goes with the annihilator of the vector field due to the dimension of the cotangent, but when it gets bigger, it does not fit, it's bigger, so the set of elements that will vanish is smaller, yeah, something like that. Yeah, more or less.
Yeah.
Okay. Okay, so anyhow, thank you.
Okay.
Doesn't matter.
So let me see now. I think I have to delete this. Okay. And okay, so what about the wiggly Lagrangian condition? Because what I described is isotropic, so now wiggly Lagrangian, actually you'll ask an extra condition on this. And this condition has to do with the kernel of the map you have. So you will be asking that actually there is something in that kernel which is L perp intersection Tm. And I must say that actually like the weakly Lagrangian condition, like apart from isotropic, is not so well integrated. Like it always feels a bit like an addition there to like an extra thing. Okay. So let me now look at the extremal cases. So in the same way that we said Dirac intersects Tm in 0 or intersects T star M in 0. Okay, so now if you have a weakly Lagrangian that intersects wedge k T star M on 0, then it's not going to be necessarily multisymplectic, okay? It's going because you could have some E, which is not the whole thing, okay? When it is Lagrangian, you recover multisymplectic, but in this case, you recover something a bit more flexible, okay? Slightly bigger. What it does recover precisely is that when the intersection with Tm is 0, then you do recover graphs of higher Poisson. And there are some subtleties to this story that I'm going to highlight here, because I'll tell you like the good and the I mean not so good. No, actually, like these are interesting questions that I still have. So there is something about restriction even at the linear level. I'm not talking about somehow pulling back a structure to a submanifold and being worried about clean intersection. No. Even at the linear level, if you have a weakly Lagrangian, okay, and you somehow put it back to your subspace, a linear subspace, it won't be necessarily weakly Lagrangian. We have examples where that doesn't happen. So this actually, yeah, it's a bit mysterious whether there should be another notion there, like it actually captures that. B fields, okay, this somehow, of course, here, yeah, B fields are not two forms anymore because they are going to be higher forms. Okay, in the Tm plus T star M, you can just with a two form send x plus alpha to x plus alpha plus ixb, and you get a one form. So now, okay, you'll need actually k plus one forms. You can define them, and the thing is that in general they do not preserve weakly Lagrangian. There is some sort of case classification, some cases where it actually preserves weakly Lagrangian. Some of them are preserved, some of them are not preserved, some of them are like something different happens. And actually there is a concept that we highlighted, but it's still, I don't think if it's where it's fully understood, is there are some cases that are a bit special, which are like this standard. I mean, the special cases would be the non-standard cases, okay, that are a bit pathologic if you want. So that is when you have like the double annihilator of phi equal to E, which happens actually when the dimension of E is either n the total or up to n minus k. Okay, this has to be, of course, with this n choose k, which is the dimension of the wedge k T star n. Okay. This condition seems to play some sort of role there. For instance, you can characterize Lagrangian as being a standard and having this AL as the full thing, as the annihilator of E. Okay, so this is weakly Lagrangian. This is still linear algebra. Okay, now let us see what integrability means. Now let us go to the geometry. So before, for Dirac structures, you have that integrable distribution, and on the leaves you will have a presymplectic form on each leaf. Okay, so now we have an integrable distribution. It is because the bracket is still like projects to the leaf bracket. Okay, but what structure do we get on each leaf? So here, the thing you have to do to describe this is, first of all, this AL that will become some subbundle on each leaf will be a subbundle of wedge k of T star M restricted to O. Is not, okay, it's not like the T star of the leaf. It's T star of M restricted to O. And you can consider the quotient of these two things. And this is a sub-bundle, the quotient bundle over the leaf. Now, the epsilon we have before, okay, will restrict on each leaf to a map that takes, remember, before it was just going from E star, from E to actually this quotient somehow. So now I'm just translating that in the language of the leaf, okay? So instead of being an element of E star tensor, this thing, so it's going to be an element of T star O tensor, this thing on the leaf, okay? That's just translated what it means. And before, in order to ensure that that sort of graph was Lagrangian, I needed that property of being E skew, okay? That when I take some contraction with an element of E, whatever I get is skew on E. So here I can do the same, but with TO, which is actually E over the leaf, okay? So here you have this condition to ensure that what you get is Lagrangian. Now, this space here, by this I mean elements that what you take is, if you apply them to an element of TO, they give you an element of FO, I will denote them by omega 1 O FO, okay, which are just like one forms on O with values in FO, and if they satisfy this extra condition here, which I need for the graph to be isotropic, then I denote them as skew. So I have omega 1 skew on O with values in FO. So now the question is, okay, you got this device here. Is this closed in any sense? What is this? Okay, this is actually the structure that you get on each leaf. It looks like this. Why? Because you have all this freedom with this AL thing. Okay, so once we look at what happens at each leaf, we can at least write straight away what the integrability condition is, which is you will need E integrable, as I said. You will actually need that these leaves, when you consider the sections of this AL, this subbundle, will be invariant by leaf derivatives of the vector fields of your leaf. And also for each leaf, you'll have a condition like this. Okay, so this is the first integrability condition. Of course, this wasn't so satisfactory, especially because of C. What is this C condition? Okay, but if you look at it, it actually looks a bit of like a formula for the for the differential.
Dogma, yeah.
Yeah, the thing is that you have to write it in terms of the epsilon.
Epsilon, yeah. I mean,
so usually you would say, I mean, this is what gives you in the other case that actually epsilon is closed, right?
Yeah. Mm-hmm.
Yeah, but what is the differential here? What is the differential in this T tensor FO? Okay, so now you can generalize this this bundle and fit it into a complex and consider just these sections of wedge PT star O with values in FO. Okay, these are just P forms on O, P forms on your leaf with values on this subbundle that actually satisfy this skew condition. And you can define, here I put it very easy. It says there is a natural delta. It's not that easy to define. To start with, because on FO, actually the exterior derivative is not well defined. But it turns out that the Lie bracket, the Lie derivative, it is well defined. And the operator IYD, like contraction exterior derivative, it is well defined. So you have to be careful with that, but then you get that there is such a thing, which is actually a differential complex, turns these skew symmetric forms with values on this bundle, this FO, into a differential complex. So that third condition, this is C, the idea is to write it as that the epsilon O will be closed. And not only that, also the restriction map, okay? And here, what you have to do is remember that this FO is it was wedge KT star M quotient by AL. Again, if I only look at the elements that are tangent to the leaf, the AL will always vanish. So doesn't matter what representative of the class you take, that if you are looking on the leaf, if the result is the same, that means that actually you have this sort of restriction, or that is actually kind of a projection. It becomes a projection, okay? But you restrict to the elements of your leaf, the FO will become a K form. So since you already have a here a bullet, okay, your form was of bullet degree, so you get bullet plus K just by restricting this thing to the leaf, okay? And this is a chain map. So this statement, the second statement, seems a bit like cheap, like right now, like random. But I will now say why it is actually important. The second more even than the first almost. Okay, so condition C becomes that each leaf that you have from your integrable distribution will have this form epsilon O, which satisfies being closed for this upgraded differential complicated. Okay. Of course, when you are in the case k equals 1, it all is exactly the same as what happens for Dirac structures. Now, the fact that this restriction is a chain map, what it's telling you is that actually we also have a map, okay? This map from the skew to the plus k, and actually it commutes the diagram. What's telling you is that this epsilon O, which is all the information you have, you can just stay with a bit of it. And if you stay with a bit of it, what you get is actually a like K presymplectic form on your leaf. Okay, but there is more information to it, which is the whole epsilon O. But in particular, you get, if you want, what you could have thought is the analog of the presymplectic form on the leaves of the Dirac structure. And because it's a chain map and everything commutes, so actually you would get that it is closed on that leaf.
A foliation, very presymplectic, yeah?
Yeah, there is a foliation, and on each leaf of the foliation, you have this epsilon O, which you can think of as a refinement of a K presymplectic structure, a multi-presymplectic structure on that leaf.
Okay, so it looks like one could expect. Yeah, nice.
Yeah, I mean, well, I would say you could expect the multi-presymplectic.
Yeah, yeah.
I didn't expect the refinement, and that the refinement would work.
Yeah, sure. There is a little bit more. Yeah, sure.
So, okay, and let me just finish now by mentioning the integration of higher Dirac structures, because what I said, okay, we've managed to fit higher Dirac, but higher Poisson into higher Dirac, but the thing was, we did all that kind of because we said, no, the good concept of higher Poisson is the concept that actually is able to integrate a higher symplectic groupoids. Okay, so now somehow what's kind of confirming that it was, for instance, at least for us, the right choice is the fact that actually that also works at the level of Dirac and higher Dirac. So actually, these higher Dirac structures will be integrated by these multi-presymplectic or K-presymplectic groupoids. Okay, in the sense that it says here that when you have a K-presymplectic groupoid with some Lie algebroid A, you will have a higher Dirac structure, and also the other way around, when you have a higher Dirac structure and the underlying Lie algebroid is integrable, okay, you have to make sure here all the technicalities of integration of Lie algebroids are satisfied. So then also you go to source simply connected Lie group integrating it, then it will become K presymplectic. And actually, okay, there is this technical condition here, which I'm not going to stop on, okay, but it actually works quite well there. So just to conclude, it's a common framework, okay, for multisymplectic higher Poisson, which is somehow what would come if you take field theories, you go to multisymplectic, and now you consider constraints and symmetries, and you get higher Poisson. So you fit everything there. You have a geometric meaning because you have these leaves where you have this refinement of a multiple-symplectic structure, and also fits the integration, if you want, motto, like to say, okay, like in the same way that happened for Dirac structures, that happens for higher Dirac, like Dirac and presymplectic groupoids. So here it happens for higher Dirac and K presymplectic groupoids. And it can also be extended if you want. Okay, the paper is written just for this case, but actually this is can be done like to incorporate polysymplectic, polypoisson. Actually, you could even put there, like if you want, like some flat bundle, even with a partial flat connection. And I would say that there are some still like mysterious points, as the ones I said that, okay, all these conditions that it seems they don't seem to fit exactly, okay, what's behind them, what's behind this restriction not being weakly Lagrangian, and it's still, I would say, largely unexplored. Here, let me mention this recent work that I think is like, the most recent, and perhaps, the contribution that goes more along these lines about graded Poisson and graded Dirac structures by Manuel de Leon and Vaquero. And if you ever want to know more, so I would say, like, the best thing the best place to look at is the paper, and you can write me if you have any questions. And that's all. Thank you very much for your attention.
Dziękuję bardzo. Gracias. Thank you. So, is there any other question, remark?
I have maybe a question.
Sure.
Well, first of all, thank you for the talk, and I would like to know, because you mentioned that you have technical problems when you try to restrict higher Dirac structures, right? Maybe I
Yes, even at the linear level, I mean, it's not like it's more like, you don't get, say, wiggly Lagrangian automatically. So okay. When you take a higher when you take like this linear version of higher Dirac, and you get you go to a subspace that is not necessarily wiggly Lagrangian.
Okay, could you maybe, like, I don't know, go a bit in detail, not so much, just
I mean, I should go to, I think I'm still right, sharing the screen. It is somewhere here. Let me there was a lot of examples. Let me, because I don't know if I have here. Look, now, okay. Don't know if it's so much visible or not, because I went full screen. Okay, here probably better. So you see, when there is, like, this is just linear algebra, okay? So I mean, it's just that the subspace need not be weakly Lagrangian, and you can see it by an example. Like, I don't know if we say what's happening exactly there. I mean, now that I was reviewing this, I think it's a really good question to see what is this larger category where actually the restrictions of this fit, because actually this is something I should have expected before to say, no, we want somewhere where if I take restrictions, I also get something weakly Lagrangian. So is this example 3.11? I'm sorry, I cannot say something else that is very illustrative. It's still a question to me as well.
Okay, thank you. I was wondering, because we are working right now with this sort of point of view. classical field theories. And what we find more useful is like the dual point of view, in the sense of instead of taking the projection onto the tangent bundle and then taking whatever map you get onto the forms, you get you do like the other way around. You study the projections onto the space of forms, and then you get whatever map you get onto the tangent bundle.
Okay.
Propose it on the tangent bundle. And from this point of view, it's sort of natural to restrict the stuff to submanifolds, because then you just need to ask for whatever you take those forms whose value of this map are tangent to your submanifold.
Yeah, but when you do, so sorry, when you do that, so I mean, still, like, if you take, yeah, I mean, if you would consider something like this, like Willy Lagrangian, here actually this example is linear algebra. I gather you can upgrade it to a manifold. So then you say, when I go the other way around, and you say consider the projection of the decay forms, and you go to the tangent. Okay, but somehow, I mean, at the same time, you are still looking at the projection to the tangent, right? To look at the leaves, or not?
This would be the image of this map.
Yeah. So.
But you quotient out this the intersection with the tangent.
Yeah, sure. Yeah, it's the same. Like is the analog picture, sure, of how you do this thing of the graph. Yeah, and you say that in that case, when you restrict,
it's at least from the point of view of classical field theories, it feels more natural, because it's equivalent to give a higher Dirac structure in this sense and to give this sort of map. Then, well, integrability is not so clear, but sorry, being weakly Lagrangian is equivalent to this map being skew symmetric. Contracting with the image of one onto another is minus contracting with the image of the another onto the first one. And then this translates well onto restricting stuff. Maybe it could be interesting to see whether how is the equivalence between restricting from this point of view and restricting from the other, right?
I mean, you should definitely then test this example that we have here, because somehow from what you are saying, I mean, I find it interesting, but if you say that, yeah, everything from the other point of view actually restricts, and here we are claiming that there is something that doesn't restrict, maybe the way that we do the restriction is not the same.
Exactly.
That may be it. I don't know. Here, actually, what we are considering, I think it was the restriction, like as you would do it for Dirac. Yeah. What does it mean to restrict for you? Yeah, I guess I really, I mean, I'm keeping in touch. Actually, I would be glad to hear. But test it with this example, 3.11, and see what happens there. Yeah.
Keep that in mind. Is the article with Nicolas?
Yeah. This is the article with Nicolas and Enrique. Yeah, 3.11 in that article. So yeah, your dual basis. Actually, because E0 epsilon, yeah, epsilon is like this. Yeah, now I don't know if I will be so fast to do it on the spot. Yeah, so
yeah. I'll make sure to take a look at it. Thank you.
Yeah, you wanted to. Yeah, okay. Yeah, thanks for the comment. Yeah, it sounds intriguing, which is good.
Okay, so are there any more questions or comments here? No? Okay, so thank you again, Roberto, for your nice talk. And thank you all for attending. Our speaker next week is Vera Vertesi from the University of Vienna, who will give us a gentle introduction to open book decompositions. So see you all next week. Thank you.
Bye.
Thank you. Bye. Yo, Manuel.